Hello, my name is Simon Filiatro. I have been interested in science since a very young age and curious about climate, energy, and the environment for more than 30 years. I am no climate scientist, but like anyone who studied science for most of its life, analyzed data on a weekly basis, I can surely study, analyze, and display climate datasets in a comprehensive manner. The goal of this presentation is to have an historical perspective on climate, CO2, and its role for the Earth and us living on it. I will only scratch the surface on two topics, CO2 and temperature, from an historical perspective. My hope is that this will be enough for you to ask relevant questions when it comes to climate and see beyond simplified statements for what they are. So here's an introduction to CO2 and climate, an Earth history point of view, and the role anthropogenic CO2 plays. The target audience here is anyone who went through high school and is not a climate expert. So let me start by explaining big words as I go. First one is anthropogenic, which means in this context, CO2 or climate change from or caused by human activities. For example, by burning fossil fuels. Let's start by looking at the concentration of the guilty molecule CO2. CO2 is quite natural and not a pollutant. Animals and plants breathe in and out this molecule, which we could not live without. I said guilty because if you read or watch the media, it seems like this molecule is destroying or forcing the climate to go out of control. Let me start with something that annoys me deeply, before we jump into actual datasets from NOAA. I don't like climate change, or global warming, or other headlines similar to this in the media, without clarifying anthropogenic CO2-induced global warming or climate change. Without this very important clarification, anthropogenic CO2-induced, we are assuming that CO2 from human sources is responsible for what those articles talk about. In the last few years, we have seen that almost anything can be caused by climate change, like hurricanes, up to more violence to women. The assumption is that the human part of the atmospheric CO2 is responsible for all those calamities. Those type of assumptions drove some people to say that climate change or global warming does not exist. Again, there's the assumption that they talk about anthropogenic CO2-induced climate change or global warming. Then this is picked up by the media accusing those people of deniers of science and other bad names. If the right language would have been respected in a scientific matter, we would not have got into those useless name battle. Okay, so let's go on with it and put some perspective to help us understand a bit of the science and data behind all this. On this slide, I will ask the following question. How does today CO2 concentration compare to Earth history levels? To do this, I went to the NOAA website, downloaded 3 different datasets, which are a bunch of numbers, put those in a software that can graph it, in this case Excel, and graphed the level of CO2 for 3 different periods of Earth history. The first graph shows the concentration in ppm, which is part per million, since 1959. Those measurements were taken in a Y on top of Mauna Loa. This graph showed the annual or yearly mean. So we see here that for the last 55 years, the concentration of CO2 in the atmosphere went from around 316 ppm up to 400 ppm. According to the more alarmist, anything above 350 ppm is dangerous to life on Earth. We reached that level at around 1980. I just want to take a moment here to explain what is 400 ppm. This is 400 molecules of CO2 in 1 million. This is a mere 0.04% of the total amount of molecule in the atmosphere. Assuming above 350 ppm is dangerous, this means that 50 ppm from 350 up to 400, or 0.005% of CO2 in the atmosphere, is causing all sorts of climate changes. And we are assuming that this 0.005% increase is from human and that we can do something about it. Okay, let's now take a look at graph number 2 on that slide. I need to scroll a bit to the left here. Now we see the second data set I graphed, which represent the last 414,000 years. This data set is from the Antarctic ice core in Vostok. What they did is drill in the ice and extract what they call carots and analyzed the air bubble in the ice. The deeper you are, the further in time you measure. From those bubbles, they can read CO2 level. A lot of people doubt those results, but let's assume that they are close to reality. So for the last 414,000 years, we have been between 180 ppm to close to 300 ppm of CO2. We see some cycles in this graph, which is interesting since nature seems to have natural cycles affecting CO2 concentrations. You can see here that I chose the same scale for those two graphs, from 0 to 450 ppm. It's important for what it's coming. Okay, now let's see the last graph on this slide. This will take a bit more scrolling and zooming, so bear with me a second or two. While I do this, you will see I try to align the y-axis scale to be able to compare the graphs. Okay, I got it. Now you see the big picture. The last 570 million years of CO2 concentration. As you can see, clearly, the scale of the y-axis is not the same. It's about 20 times more. The method of measurement here is a bit more complex to explain. If you are curious, point to the address shown and explore it yourself. So compared to Earth history, 400 ppm seems a bit insignificant, doesn't it? At that scale, the two other graphs almost disappear. Look at the dinosaur era, where vegetation and animal life was extremely rich and diversified. CO2 was almost up to 3000 ppm. In the previous era, the Paleozoic, this is where vertebrate life began, with up to 8000 ppm. 20 times more than today. Interesting contrast. I also added the approximate time span of the Ordovician era, where the corals appeared. Interesting to note that they started to appear in an era where CO2 was above 5,000 ppm. And supposedly today, with a few tenths of increase in ppm of CO2, they are all in danger by supposedly increase in seawater acidification. You may have noticed on the lower left another small graph. Let's zoom in on it. This one is interesting in many respects. First, it shows a mix of timescales from three different things. First, one is the ice core studies that I have shown before for the past 800,000 years. Second is the Mauna Lea atmospheric measurement of the past 55 years. And third are predictions. In science, you cannot mix on the same graph different studies from different datasets of different timescales and different errors or precisions. That would not even be accepted in high school science report. But for many, it's those type of graphs that are needed to show a dramatic change, which is again not permissible and contrary to scientific methods. So let's go back to the big picture. Does this false graph is dramatic now that you see the whole picture of Earth historical CO2 level? Are you still alarmed? Now let's ask the question, how does temperature compare to Earth history? In this slide, we see long-term, in hundreds of millions of years, of climate history of the planet. On the left side, we see temperature going up in warm periods and down in cold periods in big long cycles. I drew a line of today's average temperature, which is around 14 degrees. As you can see, at that temperature compared to Earth history, this is considered to be a cold period. Many say that we are still warming from the last little ice age, which makes sense looking at this graph. The question is, are we going to continue warming like the warm period, which can be as high as 25 degrees C in average, or more than 10 degrees above today, or are we heading to a next little ice age which averages around 10 degrees C? Only time will tell for sure. The second graph on this slide shows both CO2 level and long-term temperatures. One thing to notice is that there's no evidence and clear links between CO2 level and temperature. It seems the temperature is driven by longer cycles. You know already some of those cycles, like day and night and seasons are easy to see because we lived through them in our lifespan. But longer cycles exist. Some are decade-long, like the PDO, which is the Pacific Decadal Oscillation. Others are longer, like the precession or rotation axis of the planet, happening every 26,000 years. Others are even longer, like the solar system going above or below the plane of the galaxy every 70 million years or so. So what is the effect of all those cycles added up on top of each other on the climate of the planet? Many scientists spend a lifetime on those questions. I will leave it to you to study those in details. This slide asks the following question. What's the relation between today's rise in temperature and CO2? This question is now more relevant to today's debate. So let's explore this question, one graph at a time. Let's do an overview of what we have on this slide first. 1. On upper left corner, we see the last 164 years temperature anomaly. Under this graph, we have, for the same years, the CO2 level. The top middle table is the analysis of the temperature graph to find the rate of change of each cycle per ppm of CO2. The bottom middle graph shows the PDO cycle that we can correlate with the temperature graph. The top right graph is the source graph for the top left graph. And the lower right graph shows the complete satellite temperature and CO2 from 1980. Many say this is the most reliable data set we have. Okay, let's go back to the top left graph. This graph shows the HAD-CRUT4 monthly average dataset since 1850. I averaged this graph per year to have a cleaner view. This dataset does not show the average temperature of the Earth, but rather it shows what they call a temperature anomaly. This specific dataset has calculated the average temperature from 1961 to 1990. From this average, they calculated the anomaly or deviation from the average for past and future temperatures centered on 1975. This has the effect of showing temperature after 1975 as abnormally high compared with the past. The other effect is that this will amplify or zoom in on the small differences of temperature you measured. Look at the left side of this graph. The y-axis goes from minus 0.6 degrees to plus 0.6 degrees. This is a 1.2 degrees of variation over 164 years from thousands of averaged measurements all over the world. Just for fun, try putting 4 temperature sensors around your house and see if you can have a 1 degree of precision. You should measure the same temperature since they are very close together. After this small experiment, you will see the complexity of what it means to create those type of graphs, and you will understand why so many doubt the validity of those graphs. But for now, let's assume that those measurements are good and precise at better than 0.1 degree C precision. From this graph, I plotted the up and down trends in a cycle that visually match the PDO cycle. PDO again means Pacific Decadal Oscillation. This is a cycle of temperature in the Pacific that is around 60 years long. The goal here is to find the rate of temperature change per ppm of CO2. The rate of change I calculated is for 100 years. The rate of change I calculated is for 100 years, given that the trends in red and green would be constant for that period. I also chose this because people like to see what would be the temperature change in 100 years from now. So if we scroll down a bit, we see the CO2 concentration for the same time period. This has been used to fill the table and calculate rate of change per ppm. We can see that around 1850, level of CO2 was a bit below 290 ppm and up to 400 ppm today. Now let's look at the table and analyze each cycle we see in red and green on the graph. Let's look at the 5 trends. From 1850 to 1880, we see a rate of change of 0.417 degrees C per 100 year, while CO2 went up 4.8 ppm. So this gives us a plus 0.09 degrees C per ppm. From 1880 to 1912, we see a rate of change of minus 0.703 C per 100 years, while CO2 went up 9 ppm. So this gives us a minus 0.08 degrees C per ppm. From 1912 to 1944, we see a rate of change of 1.328 degrees C per 100 years, while CO2 went up 12.6 ppm. So this gives us a plus 0.11 degrees C per ppm. From 1944 to 1976, we see a rate of change of minus 0.313 C per 100 years, while CO2 went up 19.6 ppm. So this gives us a minus 0.02 degrees C per ppm. And finally, from 76 to 2005, we see a rate of change of 1.81 degrees C per 100 years, while CO2 went up 45 ppm. So this gives us a plus 0.04 degrees C per ppm. So going back to the graph, we see that while CO2 goes up, trends vary from positive to negative. The rate of change also varies from cycle to cycle. For example, like shown here, we see that the rate of change was 2.65 times slower per ppm increase of CO2 from 76 to 2005 compared to 1912 to 1944. If CO2 was driving the temperature, like we are told, we should not have seen negative trends, and the rate of change would accelerate per ppm and not slow down, like we see today. Therefore, something else is driving the temperature. For sure, CO2 is a greenhouse gas. No one disputes that. But is it the main driver? It's clear it's not. Okay, now let's look at a possible driver of those cycles. The PDO graph. Let's try to align it with the time frame of the temperature graph. So as you can see, the uptrends in temperature in red align quite nicely with the uptrend of the PDO. Same thing with the downtrend. This is only one example of how different cycles of different systems can drive the climate. The top right graph shows the source of the temperature graph. This comes from a very useful website where you can play with the temperature datasets. The graph on the lower right corner shows us the most reliable datasets from satellite overlaid with CO2 concentration. As you can see from this graph, the temperature change according to satellite measurement showed a change of around 0.35 degrees C of change over 1980 to 2014, or a 100-year trend of around 1 degree C. You also see that the planet did not warm since 1998. It even cooled a bit. On this slide, I took the same data as the previous slide, had Crute 4, but I displayed it differently. Remember, the dataset is showing anomaly, which is the departure or difference from a mean of certain years. The mean temperature today on the planet is around 14 degrees C, which is cold compared to other era, like we saw on slide 3. So I took this dataset and simply added 14 degrees C and displayed it on a graph that shows the range of temperature that we are accustomed to see on Earth, which is around minus 40 to plus 40 degrees C. I also added vertical lines, which are not related to the time axis, to display the normal range of temperature we are living under in different regions around the globe. At this scale, and displayed this way, the anomaly, which is dramatic on the previous slide, is almost a flat line displayed this way. We also see that it becomes insignificant compared to the normal seasonal ranges around the globe. I also traced a linear regression line through the dataset, which shows a trend of 0.0047 degrees C per year, which would give us a bit less than 0.5 degrees C per century. Something interesting to note is, if this trend would be extended back in the past, we would have had a mean Earth temperature of 4.8 degrees around Jesus' time. So when someone shows you a graph and a trend, be sure to ask for how long it's valid and be very skeptical. So again, nothing alarming in this view. We can see why climate alarmists don't use this view of climate data. Take Toronto, for example. We have seasonal changes from minus 22 to plus 36 degrees C, which is a range of 58 degrees C every year, while the whole planet warmed by around 1.2 in 164 years. Quite a contrast. This slide asks the following question. From all the CO2 we have in the atmosphere, how much is from fossil fuel burning? This must be the most important questions. If all CO2 in the atmosphere is from human sources, then we could probably do something to try to influence the temperature, that is, if we saw a problem related to this temperature increase, which some people doubt there's a real issue. This is a study from Norway where they analyzed the different isotopes of carbon to find the origin of the CO2. It's very interesting to see that fossil burning sources like coal, oil, and gas would only be contributing to around 4% of the total CO2 content of the atmosphere. The 96% of CO2 found in the atmosphere would then be from natural sources. I invite you to read the details of this study. It's quite technical but interesting. So from the 400 ppm we have today, only 16 ppm is something we could control. Not very much, you will ask. We have seen higher CO2 concentration in the past, therefore it makes sense that other natural phenomena can put CO2 in the atmosphere. Think of it. If we could remove all humans from the planet tomorrow, we would, inside 5 years, which is the residence time of CO2, have removed only 16 ppm from the 400 ppm. Since we have a growth of around 1.5 ppm per year, we can calculate that in 5 years we would have 400 minus 16 plus 5. So around 389 ppm, or the level of 2010. Do you think we can really make a difference by consuming a bit less or building windmills, which by the way is contributing to building more coal power stations like we see in Germany today? But this is a topic for another time. This slide asks the following. Is there a positive effect of CO2 for the planet and humans? On the left side, we see a screenshot of a video I recommend you to look at. They grew the same plant, same environment, except one was exposed to 1270 ppm, the other 450 ppm. The result is striking. 44% overall increase in biomass. Commercial greenhouses are using this technique also by artificially increasing CO2 level up to 1300 ppm. They do this by burning fossil fuel while capturing the CO2 in the greenhouse. The reason is simple. The growing period is shorter, you get better crops quality and yield, and increased biomass harvested. Another great benefit is that a doubling of the atmospheric CO2 concentration actually doubles leaf water use efficiency. On the right side of the slide, you see two studies that shows how the planet benefited from increased CO2 concentration in the atmosphere. So the more the better. And we have seen this on slide 2, where the dinosaurs had plentiful of plants to feed on while CO2 was over 1000 ppm for most of the era. Here we are looking into this question. What are the other greenhouse gases in the atmosphere? This is another important question, since what we are told in the media is that CO2 is the most important greenhouse gas, controlling the climate. So we see here from the Schmidt study that the biggest greenhouse component in the atmosphere is water vapor at 50%. Then we have clouds at 25%. Then comes CO2 at 20%. Here I have splitted the CO2 from nature and fossil sources. Remember, fossil sources is around 4%. So 4% of 20% is 0.8%. The other 5% is from other gases and are minor absorbers. So, taking the 16 ppm from previous slide, which is the fossil part of the 400 ppm, we can now see that CO2 from humans, by burning fossil fuels, could contribute to around less than 1% of the greenhouse gas effect. We also saw in previous slides that while CO2 goes up, temperature can go down or stall for more than a decade, like we see today and since 1998. So again I ask, what can we do to stop or slow down this alarming trend? On this slide, I take out my crystal ball and try to predict the future. We often hear headlines like those. IPCC Climate Report. Human inaction to climate change would be catastrophic. Here again, we assume we are talking about anthropogenic CO2-induced climate change, right? What about the word catastrophic? The second one reads, climate change already felt on all continents and across the oceans, IPCC find. The third one, IPCC reports show action on climate change is critical. An increase in global average temperature greater than 2 degrees C above pre-industrial levels would result in further melting of glaciers and Arctic ice, continued rising sea levels, more frequent and extreme weather events. We are assuming here again that we can control climate change by controlling the small portion of greenhouse gases that is CO2, and the even smaller human-induced CO2 portion of this total CO2 that originates from burning fossil fuels. Remember slide 8? First, let's talk about the IPCC. This acronym stands for the Intergovernmental Panel on Climate Change. I could spend a full day on talking only about the IPCC, but I invite you to first read how the IPCC is described by main medias, and then read about it by critics of the IPCC like Donna Laframboise. So here's the IPCC 101. They have 3 different working groups. First one look at the science of climate change and tries to find information relevant to human-induced climate change. You heard that well. The mandate is to find the relation between human CO2 and climate change, not to study climate. The second working group is to study the impact of human-induced climate change based on the conclusion of Working Group 1. The third working group is to find solutions for limiting or preventing greenhouse gas emissions and enhancing activities that remove them from the atmosphere. So, Working Group 3 depends on conclusion of Working Group 2 depends on conclusion of Working Group 1, and Working Group 1 depends almost exclusively on climate models. The reason for that is that science and data today is having a hard time showing anything catastrophic about climate, and having a harder time yet finding the relation between CO2 and those changes, like I've shown in the previous slides. Before we jump into models, let's look at the third headline news again, but this time in detail. An increase in global average temperature greater than 2 degrees C above pre-industrial level would result in further melting of glaciers and Arctic ice, continued rising sea level, more frequent and extreme weather events. Well, remember the graph on slide 3. Let's go back there and discuss the melting of ice and rising sea levels. Look at where we are today on the geological timescale. We are still in a cool phase, still going out of the last ice age some 15,000 years ago. No wonder the Earth is warming, glaciers melting and sea level rising. We would have another 3 degrees C to warm to get to the average of 17. In the last ice age, sea level were 120 meters lower. All that ice melted and made the sea level rise to what we have today. Going back to slide 9 now on the graph of sea level rise. We are panicking with a sea level rise of less than 2 millimeters per year, while the past saw a rapid rise like we see on this graph. See how today level rise is almost flat compared to the past. What about more frequent and extreme weather events? Well, Paul Homewood did a nice job of compiling this graph. It shows a ranking of extreme weather events in the USA from 1910 to today. Do you see a trend? I don't. Let's start with the lower left corner one. I took this graph from the IPCC report itself, extended the time to 2100 and the temperature to 4 degrees C. You can see on this graph many models have been displayed with the observation from 4 datasets. I also graphed 4 lines to show possible scenarios. The green line is to show what would be the temperature in 2100 if the trend from 1998 to today was to continue. This gives us an increase of around half a degree. The other lines show the range of possible future temperature from 1 degree C to a bit more than 4 degrees C. As you see, the models are not in a clear agreement with each other, and there's a lot of those models. One thing that jumps to you is that those models seem to run hot, meaning that they do not follow very well what we have from measurements. Remember, the IPCC working group are depending on the validity of those models. If they are running too hot, would that make all other conclusions a bit more extreme and catastrophic? Let's now look at the other graph on the right. This shows 73 models from around 1977 to 2025, all those spaghetti lines. The blue square shows 2 satellite data set averaged, and the green dots show balloons dataset. Again, you see that the vast majority of the models are running too hot compared to the real measurements. I drew a line through the measurements from 1985 to match the timeline of the other graphs and show a temperature increase of around 0.25 degrees C for 2025 or 1 degree C for 2100, which correlates with the other graphics. Therefore, until the models can show that they can match real temperature more closely, and until they do not depend too much on CO2 and take into account all other Earth climate parameters, I would not put too much faith in those models. Going back to full slide view, and again, we did not demonstrate here that the small portion of CO2 from anthropogenic sources is the main cause of the temperature increase. We simply showed that the models are running too hot and do not match well the real temperature of the planet. We also showed that the sea level rise is very slow compared to the previous thousands of years. We also showed that extreme weather events are not really increasing with CO2. Imagine now how you could link weather events to 0.8% of human CO2 role in the overall greenhouse effect. This is impossible. In conclusion, on slide 2, we saw from NOAA records that past CO2 have been higher and Earth did not go into a tipping point. we saw CO2 concentration up to 20 times more than today. This is without any help from humans burning fossil fuels. We saw that during the dinosaur era, CO2 was higher than 2000 ppm. We also saw how we should not display graphic, which is what the alarmists are doing. On slide 3, we saw that past history of climate on Earth is not as stable as we have today. We saw that CO2 and temperature are not in sync together. We saw Earth mean temperature to be 17 degrees C, or 3 degrees C more than today, and warm periods going as high as 25 degrees C. On slide 4, we saw that the relation between CO2 concentration and temperature rise is not that clear. We saw that while CO2 goes up, temperature can rise, fall, or stabilize. We have seen no warming since 1998. We saw that other phenomenon, like the PDO, can drive climate cycles, and there's many others we did not explore. On slide 5, we saw that the changes over the last 164 years is very small compared to the seasonal temperature changes. On slide 6, we learned that CO2 from fossil sources is calculated to be around 4% of the total, which is 400 ppm today in 2014, thus only 16 ppm. We have learned that the residence time of CO2 in the atmosphere is around 5 years, and not many thousands of years like we hear often. On slide 7, we learned that an increase of CO2 in the atmosphere can have real benefits for nature and humans. Energy from fossil fuel was and still is the main driver of human growth and prosperity. Plants like it, and the planet is greening. On slide 8, we saw that there are more important greenhouse gases in the atmosphere compared to CO2. We saw that a large majority of those are natural and we don't have much control over them. On slide 9, we learned that all the models used by the IPCC are running too hot, meaning they do not understand well all the physical phenomenon driving the Earth climate. We learned that sea level rise rate is very slow compared to other millennium. We learned that extreme weather events are not increasing with CO2. Does this mean we have to continue burning fossil fuels forever? No. We have to pursue higher density sources of energy, like nuclear power. Low-density energy sources like solar and wind is the opposite direction humanity needs to take. But this will need more explanation. Remember that humans are evolving. Not so long ago, we were burning wood to survive. Then we found fossil fuels and developed machines, and this helped replace manual work with machines and elevated human standard of living to what we are accustomed to today. We just started using higher density sources of energy like fission and hopefully soon fusion. We are developing better technology to adapt and have less impact on nature. Human ingenuity and creativity is the solution and not the problem. We can be the gardeners of this beautiful planet and even help make it more beautiful. Hopefully this big picture view of the climate and CO2 will help you be more skeptical and less alarmed. For sure, climate changes, like we saw in previous slides. But I have no doubt in my mind that humanity will adapt. We are masters at this. Thanks for watching.